Cournot Duopoly, Stackelberg equilibrium. These are the topics of this lecture. We'll look at what a sequential game or a leader-follower game is. It's different from a static game. And in this game, one agent moves first, and we'll call this agent the leader. The other agent or agents move after the leading agent moves. And these agents will be called the followers. The leader is aware of the follower's best response. The equilibrium of the leader-follower game is the Stackelberg equilibrium, which is another solution concept that's different from a Nash equilibrium. Now, since the leader is aware of the follower's best response, it can use it to its own advantage. And so, this is called the first mover's advantage, where the expected payoff is higher than that in Nash equilibrium. So the payoff of the leader will be higher under Stackelberg equilibrium. Security games. A security game is one of the major applications of leader-follower games in engineering and computer science. And here, the followers are attackers. Examples of attackers would be senders of spam emails, computer hackers, terrorists, and enemy nation, and so on. And the leader is the defender. The leader proactively tries to prevent attacks from happening. And since in many applications, it's not expected that the leader is directly aware of the follower's best response, it uses some kind of a model to estimate the follower's best response. Quite often, the model is based on some machine learning algorithm so that it can adapt. Let's look at this leader-follower game more closely. Now, agent 2 always tries to maximize its payoff pi 2 with respect to its action A2, which is its best response BR2. Likewise, agent 1 too tries to maximize its payoff pi 1 with respect to its action A1. Let's ignore the superscript S for now. Now, suppose agent 1 is the leader of this leader-follower game. It knows what agent 2's best response would be. So for any action A1 that it takes, it knows what agent 2's action would be. That is before agent 2 has actually implemented any action A2. In other words, agent 1 can use agent 2's best response as a function of A1. Replacing agent 2's best response function BR2 in agent 1's payoff, agent 1's payoff is now dependent only on agent 1's action. Agent 1 can now maximize its payoff by 1. After agent 1 implements its action, A1, as expected, agent 2, which is the following agent, the follower, implements action A2. This joint action of both agents can be represented alternately in this manner. This joint action is at the Stackelberg equilibrium with two agents, where agent 1 is the leader, and agent 2 the follower. The superscripts S denote Stackelberg equilibrium. The Cournot Duopoly game will make the solution concept clear. Let's write down the expressions clearly for the Cournot model. Notice that the actions are now x1 and x2. Also, notice that agent 2's best response is expressed as a function of x1. This is because agent 1 is the leader and agent 2 the follower. This is the Cournot Duopoly game. The actions are the quantities of a certain good produced by two firms, which are the two agents. These are x1 and x2. The production costs are lambda 1 x1 and lambda 2 x2 for the two agents, agent 1 and agent 2. And the total quantity of the good that's available in the market is the total amount produced by agent 1 plus the total amount produced by agent 2. And that's x. X equals x1 plus x2. The unit price of the good is a function of the total quantity that's available in the marketplace, and it's expressed in this form as a straight line with a slope of negative rho. The unit price will drop as the total quantity x increases. The payoffs of the two agents are their profits. So pi 1 of x1, x2 equals unit price times the quantity that it produces minus its manufacturing or production cost, lambda 1 x1. Likewise, pi 2, the payoff of agent 2, is the unit price times x2 minus lambda 2 x2. The payoffs can be expressed in this manner too, where I've replaced p of x with a minus rho of x, and x is replaced with x1 plus x2. So this and this are the unit prices, and they're multiplied by the quantities produced by the agents minus the production costs. So I have written the payoffs clearly here. We'll compute xs1 and xs2, which are the quantities produced by the two agents at Stackelberg equilibrium, which is why I have the superscript s, where agent 1 is the leader and agent 2 is the follower of the game. The derivation will involve three steps. First, we'll express agent 2's best response as a function of x1. And instead of writing br2 here, notice that I've written x2 explicitly because it is, in fact, the action of agent 2. Then, using this function here, we'll maximize. So what I've done here is, in agent 1's payoff, I've replaced x2 here, or rather, I have expressed x2 explicitly in terms of x1. So this is just a function of x1. Therefore, pi 1 is a function of x1 alone, and doing the maximization over x1 would directly give the value of xs1, the best action of S1, which is at Stackelberg equilibrium. Lastly, we'll just use whatever we found here, XS1, we'll use it in this expression, and that'll give us the actual value of x2 at Stackelberg equilibrium. So these are the three steps: step 1, step 2, and step 3. So in step 1, which is this, what we are doing is we are going to express the best response of agent 2, the follower, as a function of x1 alone. So this is pi 2. And taking pi 2 here, I've just repeated this expression here, I get pi 2, and I differentiate this with respect to x2, which is this. Because pi 2 must be maximized with respect to x2. Now, setting this derivative to 0, I'll get the maximum. And this is what I get. So x2 is now expressed in this manner, which is a function of x1. So now let's replace x2 here with whatever expression I got here, which is this. x2, the best response of agent 2 is alpha minus lambda 2 over twice rho minus x1 over 2. The next step is to use this expression for x2 and plug it in here, and then go ahead and try to maximize pi 1 to yield the Stackelberg equilibrium action xs1 of agent 1. The agent 1 is leader. So this is pi 1. I take this expression here, and so this x2 is now equal to this. So I use this expression here. I replace x2 with this expression. I get this, and this eliminates x2. Everything is expressed in terms of x1 alone. It's quadratic now, and so pi 1 x1 is equal to this here, alpha plus lambda 2 over 2x1 minus rho over 2x1 squared minus lambda 1 x1. And then to maximize over x1, I take the derivative and set it to 0. Whence I get this value for xs1, the action of agent 1, the quantity produced by agent 1 at Stackelberg equilibrium. Now let's replace this argmax explicitly what we got here. This is it. And then the third step is rather trivial. All we have to do is replace x1 with xs1, which we obtained from step 2, and we'll get from expression 1, we'll get directly what xs2 would be. So this is what I got for x2 in terms of x1. And now all I have to do is replace x1 here with x1s. And so I arrive at this expression for xs2, and I'll replace it here. And so this is the final step of my derivation. So I have the values of xs1 and xs2 at Stackelberg equilibrium. And from these two expressions, I can always derive what would be the payoffs of agent 1 and agent 2 at Stackelberg equilibrium 2. These are uh, the Stackelberg equilibrium uh, quantities produced by agent 1 and agent 2 for the Cournot duopoly. In this graphical illustration, agent 1 is in red and agent 2 is in blue. I've swapped the colors, agent 1 and agent 2, and sorry for this inconvenience. These are contours of equal payoffs of agent 1, and this point is where the payoff is maximum. As we move further away from the maximum, the contours increase in size and they represent lower and lower uh, payoffs. This is the y-axis, which is agent 2's action, and this is the x-axis, agent 1's action. Now we know that when agent 1 is best responding to agent 2's action, the derivative of the payoff of agent 1 with respect to its action A1 is equal to 0. So del pi 1 over del A1 equals 0, which implies that the payoffs must be horizontal. So we draw horizontal lines and find out the points where these horizontal lines are tangents to the uh, these circles which represent equal payoffs. And so we locate all these tangential points and connect them together, and this becomes the best response of agent 1 as a function of A2. A2. So this is our best response curve of agent 1. In a similar manner, these are the contours of equal payoffs of agent 2. This is the place where agent 2's payoff is maximized, and with increasing size of these contours, the payoffs start decreasing. We know that agent 2 will maximize its payoff pi 2 with respect to its own action A2. Therefore, del pi 2 over del A2 should be equal to 0. Whence, we draw vertical lines. Since A2 here is the y-axis, we draw vertical lines and locate the points where these vertical lines are tangent to these equal payoff contours and locate these points. Joining these points together, we get the best response curve of agent 2 with respect to actions of agent 1. So this is the best response of agent 2. At Nash equilibrium, we know that the best responses of both agents must intersect because both agents are simultaneously playing their best responses. So this is the Nash equilibrium point. Now let's look at the Stackelberg equilibrium, where agent 1 is the leader and agent 2 is the follower. Now agent 2's best response to A1 is this blue line, and that's a function of A1. So A2 is merely a function of A1. Now A1 is the action of agent 1. When agent 1 is the leader, it will try to maximize its best response. So we locate the point where this best response of 2 to agent 1 is tangent to um, a payoff contour of agent 1, and it's this point. So this point here is the Stackelberg equilibrium of the game with agent 1 being the leader and agent 2 the follower. And note that this is the Nash equilibrium point. This is the Stackelberg equilibrium where agent 1 is the leader. And at Stackelberg equilibrium, this is the point where the payoff of the leader is highest. You see that at Stackelberg equilibrium, the payoff would be higher than at Nash equilibrium because agent 1 is the leader. And that's called the first mover's advantage.